Hello everyone. We will solve another example about the calculations of the transformer. We will try to calculate equivalent circuit parameters first of all, then the voltage regulation, and finally efficiency will be calculated. So let's start with the given values. So we have a 10 kVA, 224 to 896 volt transformer. Some parameters of open circuit and short circuit data are given. For example, open circuit current, open circuit power, short circuit voltage, and short circuit power, because these values will be obtained after the experiment which we defined the open circuit voltage and the short circuit current. So how we will define open circuit voltage and short circuit current? We will examine the test sites. So for the open circuit and the short circuit tests, both of them are applied from the high voltage side. Why? How we understand this one? For the open circuit test, low voltage side is open circuited. So we have again our simple figure for the transformer, and our transformer converts 224 to 896 volt, and the low voltage side, which is the primary side of this transformer, will be open circuited. So that means we will refer our all parameters to the secondary side, and we will use the secondary side to supply the transformer. So because of this, 896 volt must be the open circuit test voltage for this transformer. Similarly, for the short circuit test, again we will short circuit the low voltage side. That means we will study on the secondary side of this transformer, which is the high voltage side. So because of this, our total output power, rated output power value, which is 10,000 volt ampere, divided by rated secondary side voltage, if we will use the secondary side to source the transformer, 896 must give us the short circuit current of this transformer, which is 11.16 amperes. What about the parameters? So if we are working on the secondary side, from the open circuit test, we can calculate RC prime and XM prime, because we will work on secondary side and their original place is primary. So we need to refer them, their values, or we will find their referred values on the secondary side. Similarly, for the short circuit test, we can calculate initially the secondary equivalent of series resistance, which represents the winding resistance of the transformer, and leakage reactance of the transformer can be calculated, which are referred to the secondary side. So let's calculate according to this analysis. We can start again with the open circuit test data, and we can calculate RC prime with the standard voltage, current, and power equations. So for the RC prime, for the core resistance, we can use the voltage square over power equation. Why? Because it's parallel connected with the source. So V square R over R can be used to calculate RC prime. And after that, again, by using the Ohm's law, we can calculate its current. The current flowing through this resistance, core resistance, will be voltage divided by the resistance value. And according to our values, we can also calculate this IC prime, which is the core resistance current. And we can use the magnitude of the current relation. How? Open circuit current will be the total current flowing through the excitation branch, total current. And IC, as we said, it is the core resistance, which is the resistance of the parallel excitation circuit. and the remaining part, which represents the imaginary part of the current and which is flowing through the XM. So that means 2.39 amperes will flow through the XM, which is the magnetizing reactance on the excitation branch. And finally, using the open circuit test results, XM prime can be calculated, and it will be 374.8 ohms. Okay, that's 4 parameters, and most important ones are RC prime and XM prime are calculated according to open circuit test results. Next one should be the short circuit analysis. So using the short circuit test data, let's calculate the remaining 2 parameters. What are they? Series connected parameters. So for the short circuit test data, we can start with the calculation of the impedance, which will be the short circuit voltage and the short circuit current, which is the total impedance of the circuit. During that case, we neglect the excitation branch for the calculations. So 14.3 ohms will be the impedance. And after that, the resistance can be calculated, which is the equivalent secondary side referred copper losses represented in the circuit. Short circuit power divided by short circuit current square. And from the short circuit test data, we can calculate them. And it will be 2.5 ohms. And from the short circuit test results, finally, similar with IM calculation, we can calculate the X equivalent as, and it will be 14.3, which is the total impedance square minus 2.5, our equivalent secondary side square under the square root, which will give us 14 ohms for the secondary side equivalent reactance, leakage reactance. And according to that, the good part, we have all the secondary side components, RC prime, XM prime, R equivalent secondary, and X equivalent secondary. So let's draw the equivalent circuit, which is referred to the secondary side and which is referred to the high voltage side for this example. So if we draw the approximate equivalent circuit, we should start with the excitation branch, which includes RC prime and XM prime. Then our series resistance and leakage reactance will come to the circuit. And we are using the secondary side voltage level for this analysis. And according to our calculations, RC prime is 7,298 ohms, XM prime is 374.8 ohms, R equivalent secondary is 2.5 ohms, and X equivalent secondary is 14 ohms. Okay, so this is the high voltage side, which is the secondary side of this transformer. So let's repeat this equivalent circuit drawing with the parameters for the low voltage side referred case. So our circuit diagram will be exactly same. That means we should start with the excitation branch. Then for the series part, we have the resistance and the reactance. Now where voltage level is the low voltage side, which is 224 volts. So if we are working on the primary side, we should use the primary indices. So RC and XM must be used because their original place is primary. And similarly, we must use our equivalent primary and X equivalent primary. And we should clarify the values of these parameters. So what we need the primary equivalents. But we have, until now, in terms of values, we have the secondary side values. So we need to refer them to the primary. We will carry them from secondary to primary side, secondary voltage side to primary voltage side. So because of this, in that case, we have to multiply the secondary side values with A square. What is A? Turn ratio. So for all these parameters, RC, XM, our equivalent primary, X equivalent primary can be calculated from their secondary equivalents. RC prime, XM prime, our equivalent secondary, and X equivalent secondary. How? By multiplying with A square. What is A? 224 over 896 volts. So 224, 896 volts for the A, which is the turn ratio square. So which is equal to 0.25. So from here, we can calculate their values. The first one, which is RC for the primary side, will be 456 ohms, 23.4 ohms, 0.156 ohms, and the last one will be 0.875 ohms. So we should clarify the equivalent circuit with the values of these parameters, and we can obtain the full equivalent circuit for primary and the secondary referred cases. And then we can calculate the voltage regulation to examine the performances of the transformers. So for this transformer, let's examine the voltage regulation for our standard load characteristics. So voltage regulation, of course, at full load and at 0.8 power factor lagging. At the rated load, we have 0.8 power factor lagging load. So for the voltage regulation, we need secondary side full load and the no load values. And as we discussed previously, no load secondary side voltage means Vp over A, which represents the primary referred to the secondary side, and which includes the losses, voltage drops, addition to the secondary side rated voltage. And for this equation, we need to calculate, first of all, the secondary side rated current. And for secondary side rated current, we must use our power value, which is 10 kVA, over 896 volts, which is the rated voltage, and the magnitude of the current will be 11.16 amperes. And we must add the power factor characteristics, the angle to the magnitude. So because of this, the secondary side current will be 11.16, and for the angle, cosine minus 1 of 0.8 will give us 36.9. And because of the lagging word, we must use minus in our current expression. Okay, now we can calculate Vp over A, which is equal to secondary side no load voltage value. So it will be Vs, and the voltage drops of the series connected components in the equivalent circuit. So our equivalent S times IS, which gives us the equivalent resistance voltage drop, and similarly leakage reactance voltage drop must be added. For Vp over A, Vs, it is the rated voltage of the transformer, and it will be our reference for our analysis. And the secondary side, our equivalent, is calculated as 2.5, and we have calculated the current, which is 11.16 with minus 36.9. Then the complex part will come with 14 ohms and with the current. Okay, now we should go one step further to clarify the voltage drop values. So 896, and it will come 27.9, which is the multiplication of the coefficients of the R and I magnitudes, and with the same angle. Then for the leakage reactance voltage drop, the magnitude will be 156.24, and the angle will be 90 from the complex operator, 90 minus 36.9, which is 53.1 degree. And from here, you can calculate the Vp over A as 1017 with 6.1 degree. And by using the Vp over A, by using the secondary side no load voltage value, voltage regulation can be calculated for this operation conditions. So at full load with 0.8 lagging power factor, it will be 1017, which is the magnitude of the no load voltage value, minus 896 over full load voltage value. As a percentage, it will be 13.5. Okay, so we have the secondary side no load and the loaded voltage values with the angles, and we calculated the current magnitude and the direction we determined. And in addition to that, we have calculated the voltage drops of the resistance and the reactance. So for the AC systems, it is easy to represent the voltage regulation issue with the phasor diagram. So let's try to draw a phasor diagram according to our calculations. And we will start with the Vp over A expression. So we will try to obtain these parameters with the arrows. So for the Vp over A, we will start with the Vs voltage drop, because our equation includes Vs and the voltage drops on the resistance and the reactance. So our two fundamental inputs for the phasor diagram will be Vs, which is the reference, and the magnitude with the angle can be clarified. Then the current, we have a lagging power factor. That means we have a negative angle. It's coming from back, 36.9 degree, and IS with minus theta, which is the power factor angle, and the value is 11.16 with minus 36.9 degree. Okay, so we started with Vs. Then let's continue with the resistance voltage drop. It must be parallel with the Is, because we will multiply the Is value with a constant of resistance. So the black arrow will represent the resistance voltage drop, and according to our voltage regulation calculations, it will be 27.9 with minus 36.9. Then the next one will be the reactance voltage drop, leakage reactance. So initially we must rotate 90 degrees from our direction. The reason of this one is the complex operator. And after we turn 90 degrees, our angle with respect to reference will be 53.1. So the red arrow represents the reactance, leakage reactance voltage drop, and it will be 156.24 with 53.1 degree. And finally, our left side, Vp over A can be obtained. Its value is 1017, and its angle will be 6.1 degree with respect to reference of Vs. So here we have the angle of 6.1 degree. Okay, this is the phasor diagram of the transformer according to given operating condition. Now, finally, let's calculate the efficiency of this transformer for same characteristics, for same operating condition. For the efficiency, we need two parameters. Output and input powers must be determined. So, for the input power calculation, we need to determine the losses. So, let's start with the power and the losses. Output power. Again, as we discussed earlier, we can use S rated, which is the given volt ampere value of the transformer, 10,000 times cosine theta can be used. Power factor. Or you can use 896 times 11.16 times cosine theta, which is 0.8 also. Both of them must give you 8 kilowatts for the output power. After that, let's calculate the core power. Core losses of the transformer. For the core losses, we can examine the RC. Why? Because RC, the resistance of core resistance, represents the core losses in the circuit. So for core losses from primary or secondary side, we can use the equation. Let's use the secondary side equivalent, secondary referred case, because it's commonly used in the analysis, because efficiency, voltage regulation, and phasor diagram analysis, all those parameters are important for the secondary side performance of the transformer. So because of this, let's use Vp over A, which is the secondary side input voltage, secondary side referred circuit input voltage of the transformer. So for the secondary side, look, the resistance must be RC prime, and according to our calculations, we know the Vp over A and RC prime. So 142 watts will be absorbed by core losses, core resistance. Then the last loss for the circuit will be the copper losses, which is represented by our equivalent in the circuit. Similarly, let's use the secondary side equivalent. For the current, our magnitude is 11.16 and the resistance value is 2.5 ohms. So 311 watts will be consumed by our equivalent. And finally, the efficiency can be calculated. So the general efficiency equation we will follow: output power divided by output power and the losses for the system. So from here, we can find the efficiency of this transformer as 94.6%. Thank you for watching.